All right, so starting now, this is what's going to be available to you via video I'm going to post at the end of the session here. So again, you can try to keep up with me on SOLIDWORKS, but I suggest you just watch and listen, and then when you're ready to push the buttons, you go back on, watch the video. So let me, all right, so Alex has the same question, or same request about weekend, so just send me an email, and I'll take the poll and see what day is best for everybody. All right, so let's go look at the instructions. And so the videos are very useful to teach you about GD&T, but they're not so useful in to teach you how to do the assignment. And so if you watch the videos only and don't read the instructions, then you're not gonna fulfill the requirements of the assignment. So make sure you watch the videos that are already on Blackboard, already on my YouTube channel, and follow the logic, but don't expect that assignment is going to show you, or that video is going to show you how to create your correct assignment. The way you need to go approach the assignment is to read the instructions. And I'm going to poke around here and find, that's not it, that's from a previous semester. So we'll go here, assignment 5. So somebody help me out here. Where's the instructions for the assignment? I think this is it. So this is assignment 5, geometric dimension. This is on Blackboard. So the first steps is download all the data. This goes for every assignment. When you start a new assignment, don't start doing CAD stuff. Start figuring out what it is I want. So go in, download all the files on Blackboard. Read the lecture slides. I get a lot of questions during the week, during office hours. And all the answers, not all of them, but a lot of the answers to the questions are contained in the lecture slides. So if you're not reading these lecture slides, you're missing out on a lot of answers to your questions. So review it. So this is the first 2 bullets. Review and understand the GD&T summary file. So that's another file that I posted, and it's beyond extremely useful. It's the best one-page document to understand how to do geometric dimension and tolerances. So I would make sure to download this file, put it in your A05 folder under a subfolder called handouts, and refer to this from now until the end of time, because this is great information. It's got notes and stuff on the left and right sides. This is all stuff coming from ASME Y14.5. It's got all the geometric characteristics listed. It's got an example of a drawing call out. It's got a picture of determining what the tolerance zone is for the particular characteristic. And it tells you things like MMC, LMC, datum used. This is extremely useful to me because I could tell everybody to go buy a copy of ASME Y14.5, and then $250 later you'd read it and you wouldn't have any idea what to do. This is a very detailed, condensed document that really gives you a lot of insight. And so if you're trying to remember how to do GD&T in the future, I highly suggest having this as your first reference point. So please look at that file and use it as you're working through this assignment. All right, so that's what the bullet says. Review and understand GD&T summary PDF file. Retrieve assignment details from Excel file. And so there's a JPEG file that I made from Excel file I made, and it's in here somewhere. And so this is the information for everybody to use. All this is going to be this is the same kind of a spreadsheet that you see often. And as I'm talking, if you have questions, stop and interrupt me and ask me the questions. Otherwise, I want to keep talking.
I you said that you were going to record the session. I don't think it was recording.
It's not recording in Zoom. It's recording in Camtasia. When I record in, I'm glad you asked. So when I record in Zoom, I never can get it to work. So I've abandoned recording inside of Zoom, and I'm recording in a separate program called Camtasia. And so that's going on right now. And right now we're at the 5-minute mark. And so unless my computer crashes, I want to download this, edit it, and post it on my YouTube channel. So I think we're good, but thanks for asking. All right, so here's your student ID. These columns are different numbers that I want you to use based on the column headers. And it's unclear what this means just yet, but we'll get to it in a minute. And you got material assigned, temper assigned, and finish assigned. So again, the point is that these assignments, I want y'all to learn how to understand about different material types and different finish types that correspond to these different material types. And I teach material courses here at Texas State. We're not going to turn this into a materials course, but I at least want you to be familiar with different alloys. So I've shown this chart multiple times, but a lot of y'all haven't been to the weekday Zoom session, so I want to do it one more time. So we're going to have aluminum alloys that you're going to be assigned. And these are the most common materials that I've used in my career as a mechanical design engineer. Steel alloys and stainless. So there's lots of more materials in these three different types, but in my experience, these are the most common. And for a course like this, where we're not really trying to teach material science, it's a good start to get you some familiarity. So you're going to be assigned during the semester, you're going to be assigned some aluminum alloys, some steel alloys, and stainless steel alloys. When you're assigned an aluminum alloy, you're going to use a finish, very, very common finish, is sulfuric anodize. Let's get the caps off turned off. You're going to have to talk a little louder. I can't hear you.
No, I said I don't need to slow you down, but what's the purpose of this?
Yeah, I'm still not hearing you. Let me turn up my volume. Try it one more time.
Yeah, I was saying that I wanted to know what's the purpose of using the temper and all that stuff, and the finish.
This is the finish, and this is the alloy. And for now, I'm not talking about the temper yet. But this is the alloy, this is the material, and this is the finish. Does that make sense?
Yeah, that makes sense. I was just asking, what's the use of the finish?
The use of the finish is if you have a part that's made out of steel and you don't finish it, in about a week and a half after the part's outside on a bridge somewhere, it's going to start rusting. And so your boss doesn't want that, your customer doesn't want that, and you don't want that. So if you have a steel alloy and you don't add a finish to it, then your company is not going to be in business very long because no one's going to buy your stuff, because after a week and a half it's going to be rusted. Same thing with aluminum. If you don't do a finish on the aluminum, it's going to start oxidizing, which is the same thing as rusting. And it's going to be a problem for your customer, which means it's a problem for you. So does that make sense?
Yeah, it makes a whole lot of sense.
Good. All right. So for steel alloys, a common finish is zinc plating. If you go to Home Depot and walk down the line where they sell chain link fences, you're going to see this stuff that looks like it's paint is dripping off the fence material. The fence material is made out of steel alloy, some kind of a carbon steel alloy. And when they sell the carbon steel alloy chain link fence and somebody installs it, in a week and a half, it's going to look horrible because it's going to be all rusted. And so what every single person that makes, manufactures, and sells and installs chain link fences that are made out of steel alloy, they zinc plate it so it doesn't rust. And so if you get assigned a material that's a steel alloy, your finish is going to be zinc plate. And if for stainless steel, it is better against oxidation, rust. It's better against it than steel alloys, but it'll still oxidize over time. And so an extremely common finish to put on stainless steel alloys is passivate. So if you look on assignment 3, the drawing I gave you, it gave you a specification for stainless steel alloys, and it gave you a specification for passivate. And so as I go through these drawings, I take off 5 points if you don't tell me a specification for the material. I take off another 5 points if you don't put in a specification for the finish. So if you haven't seen this before, I'm going to wait 10 seconds and let you take a screenshot of this, because this is going to be the same kind of thing we've been doing up till now, and it's going to continue to follow through to the end of the semester. All right. So this is where you find the information. Where's the TIPEG file? So we've gone through that. So that's how you find out these values here. All right, so let's keep going through the instructions. This is going to guide you through what I'm looking for. So we've gone through here. We've review and understand the GD&T summary. We retrieved assignment details from Excel file. That's what we just looked at. It says generate SOLIDWORKS part file, but I've changed that. I've just given you the SOLIDWORKS part model on Blackboard. So if you've not started assignment 5, or you're trying to redo assignment 5 for the red line updates, go to SOLIDWORKS, download the file that's on there now. It's a SOLIDWORKS part. Use that to make your drawing. And then you watch the videos. This goes for every single assignment. Watch the videos to find out the concepts, not how to do the drawing, but the concepts involved. Okay, so now let's go through the steps here. So I'm going to go through these one at a time. I'm going to create my drawing based on these steps right here. So I'm going to make a, let me save this. Where is it? Attendance. Okay, so I'm going to grab these so I can look at them on my other screen here as I go through. So I'm going to go through and do these steps to show you how to do it, and then you're going to listen to me, and you can try to follow along in SOLIDWORKS on your own, but I highly suggest sitting back, listening, take notes as I'm going through this, and then when you get ready to do your corrections to assignment 5, you'll use your notes and you'll use my video I'm going to post to talk about how to do this. All right, so here we go. So here's my drawing. I'm so sad somebody left because they're going to miss out on all this stuff. So I'm going to say, so I've started a drawing. And so let's open up that drawing. It's this guy right here, I think. Okay, so you already know how to do this part. You can make a top view of your part. You know how to do a section view of the part because you've done assignment 4. You need to know, you can do an orthographic projection. And so you can do an ISO view. And I haven't filled out my notes or my revision block or my title block. I'm not going to talk about that today. You've already got 4 assignments you've been done so far. You already know how to do that. And if you don't, look at the red lines. I continually keep taking off 5 points for material and finish where you don't have a specification. So I'll write on there, ask me. Ask me means come to the Zoom meeting during the week and ask me why you're losing 5 points every time you do this, because I don't want you to keep losing 5 points. All right, so here's the views that you already know how to set up. And so step 1 says create datums. Primary datum A is defined by the bottom surface of the part. So the bottom surface of the part is this bottom surface here. Right down here. That's the bottom surface of the part. You'll notice the way I built the model, I used logical planes. Here's the top plane. It's at the bottom. There's a right plane that goes right through the front plane goes this way. The right plane goes to the middle of the part. So the bottom surface, according to the first instruction, says create profile, primary datum A is defined by the bottom surface of the part. So I can do that. I can select this button here. I can select this button here that says datum feature, and I can select this bottom surface, and it looks like it wants to do B. I want to do A. So there's A. I'm going to select that edge, and I'm going to place that datum. So I've done step 1. Second step says secondary datum B is defined by the center line of the left through hole. Well, looking down from the top, this looks like the left through hole, and this is the right through hole. The small hole is the through hole, the big hole is a counterbore hole. So I need to define a datum based on the instructions. Secondary datum B is defined by the center line of this hole here. So I'm going to go up here to datum feature. I'm going to select that center hole, and I'm going to place the datum. So now I've done step 2. I've defined datum B as the center line of that through hole by doing that. Next step says tertiary datum C is defined by the center line of the right through hole. Well, that looks like this hole over here. So I'm going to go back to, go ahead.
In your video, you put datum B.
I know I did. I'm saying that the video is not instructions on how to do assignment 5. The video is instructions on how to teach you about how to do GD&T in general. So like I said earlier, if you follow the video to do your assignment, all your datums are going to be wrong. What I want you to do is use these instructions that I provided to do the drawing. And you're not the only one that did that. I got a ton of folks that followed the video to define the datums. The video is a guide to try to teach you how to do GD&T, not how to complete assignment 5.
My apologies.
No, it's not. No apologies. You're good. I'm glad you're asking questions. So as usual, Kadeem is always asking questions, good questions, and so I'm always glad to hear from Kadeem talking about questions. So thank you, Kadeem. So I'm going to go to datum feature, and I'm going to define this through hole here as datum C, and I'm going to place it over here. Oops, I grabbed the wrong edge there, didn't I? Datum feature. I'm going to grab this hole. And there we go. All right, so I did the first set of instructions says create datum. So I did that. A, B, and C datums are now defined. All right, let's go to the next set of bullets. Create feature control frames. Feature control frames is important. Important is not a strong enough word. It's the whole reason we're doing this GD&T characteristics for a drawing. So feature control frames tells the manufacturer what the design intent of the designer is, which is you, on how to fabricate the part. So the next one says create a feature control frames. So there's multiple feature control frames. Let's take them one at a time. First bullet says create profile of a surface. Well, what does profile of a surface mean? Well, I think the answer most of you have is you don't have any idea. So let's go look at the sheet that I'm excited about, that tells me all I need to know. Not all I need to know, but it's a good starting point to find out what's going on with GD&T characteristics. And so I'm going to come down here and I'm going to scroll down until I find profile of a surface. So I'm going to go down, I'm going to go down, I'm going to go down. Boom, there it is right there. Profile of a surface. Here's an example callout. There's a symbol for the characteristic of profile of a surface. There's the tolerance zone dimension. And there's the datum that the characteristic is related to. So if you use this callout on a drawing, this is what it means. It means you have two perfect contours that are 4/1000ths apart from the part definition. And so if I do a screenshot of this and find my, where's my, where is it? File at? There we go. So if my part, this line here at the top, this curve here at the top, this is perfection. This curve right here is perfection. This curve is perfection. Well, this part in the middle, that's my part, and it's not perfect. And if this thing looks pretty horrible, it looks like this. Looks crazy. But the inspector is going to look at the part and say, you know, it's not perfect, but that passes my inspection because every edge of that feature, every point on that feature is within the tolerance zone. So that means that this part passes inspection. And then, so this is a good place to go. So let's make that call out here. Well, the instructions say to create a feature control frame profile of a surface for the entire perimeter of the top view within tolerance shown on the Blackboard handout. Well, the Blackboard handout is that thing we keep looking at. It's got all the numbers. Everybody's got a different set of numbers for their student ID. So we're going to create a profile of a surface GD&T callout for that surface. Well, the top view of the part is where I'm going to see that surface. It's this whole perimeter. It's all the way around here. All the way around there is going to be controlled by this feature control frame. And so I'm going to go up here, instead of getting on datum feature, I want to hit geometric tolerance. This is how we create feature control frames. I'm going to click on that, and it's going to give me a pop-up and start asking me questions. It says, where do you want to connect the arrow to? Well, I'll just connect it right here to this surface here because I want to define the whole perimeter. So I'll just click here, and then I click to place the feature control frame, and it starts asking me, hey, what do you want to have put into the feature control frame? And so I'm going to walk around here and find the button I'm looking for. Profile of a surface, there it is right there. So if I click on that, it puts profile of a surface right there in the feature control frame. Now it's asking for a tolerance. Well, now you're going to go to your Excel spreadsheet thing that I put on Blackboard, and you're going to read what. Let's make this thing bigger. You're going to go see what your profile of a surface tolerance zone is. And so who wants to tell me their student ID?
13.
All right, 13. So Viba is going to choose 5/1000ths for her profile of a surface tolerance. She's number 13, 5/1000. So I want to go ahead and do hers. I want to type in 5/1000ths here. And now I need to tell it what datums do I want to refer to. Well, this part is defined, and you have to watch the video to understand all this. I'm not going to go through the whole video. But it has to do with eliminating degrees of freedom. It has to do with a datum reference frame. Go watch the video, and you'll see what I'm talking about. We have to define the feature control frame datum references based on that. And the way I do that is I add datums to the feature control frame. Right now it's got the characteristic, profile of a surface. There's the size of the tolerance zone. And now I'm going to say add datum. And I'm going to type in A and hit good, add a new one. And I'm going to type in B and add a new one. And then type in C and then add another new one. I've already added C. Okay. So there we go. That's the feature control frame that I'm asking for in that first set of instructions. So what does that mean? Let's go review what we just talked about. What in the world does that mean? Well, let's take a screenshot here and I'll draw some stuff up here. So what that means is that I've got perfection here. I need to define these edges with basic dimensions because this is perfection. This is what I'm shooting for. So I'm shooting for perfection. And this is going to be defined in a little bit with basic dimensions. But that's perfection. And so the call out is saying, I'll just draw it for a small portion here. So I've got a line here. This is a perfect line here. And a perfect line here. And this dimension here, somebody tell me what you think this dimension is. What's the size of this tolerance zone?
Is it 0.005?
It is 0.005. Very good. That's what that feature control frame is saying. The tolerance zone is within 5 thousandths of perfection. The blue line is perfection. We can't machine our part to perfection, but we can reference perfection. And then as long as the part is within 5 thousandths of that tolerance zone, we're good. And so if the part looks like this, and it looks like crazy, horrible looking thing, this is all good until it does that. If it does that, then the part gets rejected and thrown away because the profile of the surface is beyond the tolerance zone. And so this part gets scrapped if that's how it looks. But as long as it's within this tolerance zone, it's going to meet the requirement. So every single one of these features for this blue edge here that's supposed to be drawn as perfect, those edges need to be located with basic dimensions from the datums. So I want everybody to pick up a pencil and get your paper. I know you've already got a pencil and a piece of paper. I want you to write this down. I'm going to talk real slow. I want you to write this down word for word because this is critical to understand about the trifecta. The trifecta is when you have a feature control frame, you have to have 3 things. Otherwise, it does not make sense. And the vendors that make your parts are going to make fun of you because you don't understand the basics of GD&T. So my goal is to make sure they won't really make fun of you. But you get the point. I want you to understand the basics. So the trifecta for GD&T is number 1. You ready to write this down? Number 1 is you got to have datums. Number 2, you have to have a feature control frame, which is right here. And number 3, this is the most important part, you have to have dimensions locating the perfection, the target, the goal. The target is what's perfection, and this blue line here is perfection. So you need to have basic dimensions that locate those features, which is this whole perimeter in this case. And this is the part I want you to underline 3 times. Those dimensions have to come from the datums. The dimensions, the basic dimensions that you use for feature control frame They have to come from the datums because everything for this GD&T feature control frame has to do with perfection. The datums are perfect. The basic dimensions are perfect. And this feature control frame defines perfection for the location of the feature at hand. So let's go do it. So I need to locate this whole perimeter. I need to
Can I
locate.
ask one question?
Sure.
In the drawing, I noticed you have datum A, B, and C, but in actuality, we only put B and C in this drawing, I mean this figure. So why would we have A, B, and C and not just B and C? Just asking.
No. You're asking a great question. I'm going to go through a whole discussion here based on that question. It's a really good question. So you get this drawing, and someone hands you a drill, and they say, look at the drawing and drill those holes. You say, okay, I got it. When you pick up the drill and you look at this drawing, you look at this call out right here, what's the primary datum, Kadeem? Let me give you a hint. What's the primary datum?
Hey.
All right. The first datum listed is a primary datum. So that means you pick up your drill and you orient your drill to be perpendicular to datum A. That's what that says. And so you pick up that drill and you point it perpendicular to A, which is this bottom surface. So in this view, you know that this thing is sitting on a datum simulator, and you're going to orient your drill to be perpendicular to datum A. That's the first thing you're going to do. The next thing you're going to do is figure out where this hole is located from datum B. Well, it is datum B. So you're going to take your drill, make it perpendicular to A, and then you're going to locate X and Y from B and C, and you're going to drill the hole. Same thing with this profile. The first thing you do when you orient this part is you're going to put it on datum simulator A, and then you're going to have if you watch the video, I talk about a gauge pin, and I talk about go, no-go gauges. That's how you locate datum B and datum C. So that's the deal. This orientation has to do with, in order, you make these edges, all these edges here are perpendicular to datum A. First, that's the first thing you do. Does that make sense? Kadeem?
It does.
Okay.
It does.
Okay. So now I'm going to go add my trifecta. I've got the datums defined. I got a feature control frame here. Now what I need to do is I need to define the location of perfection, and I need to use basic dimensions to do that. And I need to dimension them perpendicular to datum A and relative to datums B and C. And actually I made a mistake here. This datum C I don't necessarily need, and so I'm going to turn off. How do I do that? So I'm going to delete datum C. There we go. This is really what I want here, for reasons that you'll see in just a minute. All right, so I want to dimension this outside perimeter. I'm still on that first step. I'm trying to figure out how to create a profile of surface for the entire perimeter of the top view within the tolerance zone. So I've done the feature control frame. I've got the datums. I got to have the trifecta. So I've got to add basic dimensions to locate this perfection relative to the datums. So I need to locate this edge over here. So I need to add a dimension to that edge. If I dimension this edge, so this will locate perfection. I'm coming from perfection, which is datum B. I'm defining perfection over here, so I need to turn this into a basic dimension. And I'm going to select it, and I'm going to say tolerance precision. I'm going to go from none to basic. And I got the box around it, so now the machinist knows, and the inspector knows, and everybody on the planet knows that this is a basic dimension, and this is going to help me define this perimeter. But I got a lot of dimensions to go. So if I want to define this edge right here, what do? Well, I add another dimension. I want to go from here to here. I want to add that dimension. That dimension comes from the datum B, and I need to make that a basic dimension. And I keep going until all of these features are defined. Now, if I do this, if I add a dimension here, whoops, smart dimension, if I go from here to here, then I make that a basic dimension. Does that look good?
No.
Why?
Because it's not referencing a datum.
Oh my God, Eddie, very, very, very good. This is not going to work because this edge is non-perfect. This edge is non-perfect. This is not going to work because this is not defining perfection from the datums. So what I can do is I can do this. I can actually get SolidWorks to behave. I can do this. By the way, Eddie, you get a gold star. That was awesome. Here we go. So I'm going to do this. And then if you leave it looking like this, you're going to lose points, right? You got to clean it up. So I'm going to go this way. I'm going to go this way. And I want to do this. I'm going to say, make this a basic dimension. How many places does this dimension apply? 364. You're on a roll, Eddie. What else should I add to this dimension at the beginning? Let me give you a hint. There's two of them. This edge is 364 down from datum B. And this edge is too. If I don't put the 2x in front of there, then I don't know where this edge is over here. So I'm going to say OK. Now you say, well, this one's not coming from a datum. This is important. Think about it. This dimension comes from a datum B, which means that this location, this target location is perfect. So if I come from this guy from perfection to this edge, then this edge here is defined as perfection. And so this is okay. This is okay, the 0.75. Eddie and I agreed that this was not a good idea. But if we add this to this, then they're both okay.
So, Professor, that kind of went over my head. 0.75 not being a good.
It wasn't good until I added this.
Oh.
This comes from perfection because this edge here is defined from perfection, which is datum B for this guy. So this guy is not okay unless you have that guy.
Can you explain what perfection means?
Perfection means there's no tolerance. So another way to do it would be this way. I could dimension from here to here. I can get SolidWorks to behave. If if I want a dimension from here to here, I could do this alternatively. I could make that a basic dimension by doing the same thing I did a minute ago. This would be another way to do it. I'm defining this top edge from perfection. This dimension is coming from datum B. And then this dimension is coming from datum B also. So this way or the other way is fine. Either one's fine. But you can't have the 0.75 by itself because it's not coming from the datum. All right, so you're going to need to go in and do all the other dimensions. You got to fully locate this perimeter using basic dimensions. And so let's go to the next. So this is not done yet. You got to keep going. But I want to move on to the next question. I want to do a positional tolerance zone for the two counterbore holes. All right. Well, we need to call out the hole first. And so I want to use my favorite annotation to say add a hole callout. You've already created the hole using the hole wizard command to create this counterbore hole. And so let me go down here and add center lines. I didn't add center lines yet. So every cylindrical feature in your drawing needs to have a center line and a center mark. So I'm going to drag that like that. There's a center mark. And I want to add a center line to this one here, between here and here. And then the center line always goes slightly beyond the end of the hole, so that looks good. All right, so I'm just going to put dimensions down here just to see what this hole is. How do I define this hole, which is the counterbore hole? I need to know the through hole diameter, so I can place a dimension here. Oops. Place a dimension here between here and here. So that's the through hole diameter. So that's the through hole diameter. Here's the counterbore diameter. And here's the counterbore depth. And this is what I've already defined in SolidWorks part model using the hole wizard. Come on, SolidWorks. Help me out here. There's that guy to that guy. Man, this is not behaving well. All right, I'm going to try it one more time, and then I'm going to give up. Smart dimension from here to here. Boom. All right. So it's 11 o'clock. I want to keep going. I got a couple of students in the hallway I need to chat with. Give me 60 seconds and I'll be right back. What's going on? All right, thanks for your patience. So I got students working on a NASA project. It's kind of interesting. So anyway, all right. So this is not the way I'm going to dimension this hole, but this is what this hole is. It's got a through hole of 169. It's got a counterbore diameter of 312, and the counterbore depth is 170. So rather than doing all these different dimensions on this other view, I'm just going to call out the hole with a normal ASME Y14.5M call out. I'm going to come up here to hole call out under annotations, hole call out, and I'm just going to select the hole and place the call out. There it is. I get it for free because I've already defined it in SOLIDWORKS part model. Do the numbers make sense? Yeah, I'm not quite sure why this is 169. Anyway, there's the through hole. It's got some tolerances on there because I add tolerances over here in the properties. So when I placed it, I selected it and I came over here and I said, I want to add a tolerance to the size of the through hole, which is one of the things I ask about from the instructions. And I come down here and I say, where is it? Call out value. I can change the tolerance on the through hole, counterbore diameter, counterbore depth. If I want to change the diameter, the tolerance on the through hole diameter, I select that one and I go bilateral and I make a plus or minus 3 thousandths tolerance. If I want to change the tolerance on the depth of the counterbore, I come up here and change it to counterbore depth, and then I can make that a two-place dimension, which seems to make sense because the depth is not super critical. So you can change the tolerances on any part of this callout. So now I don't need these other callouts down here. These other callouts are not needed because they all are defined in that whole callout.
Professor, you said that you changed it in your properties to get the, because when I do the whole call out, it doesn't.
I just select the dimension, and I come over here to this dialog box over here and change whatever I want to change. Does that make sense?
Yeah.
Okay.
I see. So you placed your tolerance in the plus and minus box, right? So you bilateral, under bilateral.
Yep. So if I select it, I go back over and look what it says. The through hole diameter has got a bilateral tolerance of plus 3 thousandths and minus 3 thousandths. If I change it to plus 5 thousandths and minus 5 thousandths, it'll change it on the call out.
Okay, I see it.
Okay. So that's the feature control frame. That's 1, 2. That's the second bullet. And it says use MMC modifier. Oh, no, I got to make the feature control frame. So I've made the call out for the hole. And now the instructions say, what? Create a positional tolerance for the two counterbore holes. Use the MMC modifier. Okay, let's do that. So I'm going to go to my button I've been using, geometric tolerance. And I don't want to connect it to a edge like I did this one. I want to tie it to a hole call out. So I want to select the hole call out. And then I want to click on the box and I want to do the same thing I did a minute ago with this profile of a surface and start selecting what I want. So the positional tolerance is, where is it? Total run out, angularity. Where's position? There it is right there. I want a position call out. And go ahead. All right. So we'll go back to Viba's number. So she's 13. It says the whole positional tolerance needs to be within 6 thousandths. So I want to type in 6 thousandths here. And the instructions also say use MMC modifier. And so I want to go down to one of these options over here and find the MMC, find the modifiers. There it is right there. Maximum material condition. Who can tell me what maximum material condition is?
It's like the most material could be on the
Exactly. How did you learn that?
slides.
Thank you. Thank you, Eddie. If you don't know what MMC is and LMC is, that means you haven't read the lecture slides like Eddie's done. Go read the lecture slides and it'll explain the basic dimensions. It'll explain a lot of this stuff. So I'm going to choose the MMC modifier. There it is right there. And now I need to add the datums. So I'm going to add a datum for datum A and add new. Datum B. Let's do all caps, otherwise I'll lose 2 points. And then datum C. That's it. The way to read this in English, these two holes need to be located within a positional tolerance with a tolerance zone of 0.006 at maximum material condition relative to datums A, B, and C in that order. That's what that means.
Can you explain how you decided to use the maximum material condition?
That's a great question. And the answer to the question is you need to take my advanced GD&T class. We just don't have enough time to go through why I chose that number.
Okay.
And it's extremely important as a designer to know how to do that. But they only give me 10 weeks to teach this summer class, and I don't have time to teach everything. But that's a great question, and you can take my advanced class to learn how to do that. And that's super important. And maybe later in the semester I'll have a quiz to talk about how to do that. But for now, we're going to say somehow Summers magically knows how to do that.
Okay,
but
thank you.
It's extremely important. And if you want to write something down, write down positional GD&T maximum material condition modifier, MMC modifier, bonus tolerance. Bonus tolerance is one of my best friends. It's a way for me to invoke my design intent to the machine shop, and it's a win-win situation. I win because my part always works, and the machine shop always wins because they get to have extra tolerance if they know about bonus tolerance. So that's an extremely good question, and we need to have another class to be able to do that. All right, so I've done that. Now I need the next bullet says create a flatness call out to the bottom surface within a tolerance shown on the Blackboard handout. So let's go back here. Vibba's got 13. Flatness tolerance is going to be 0.006. I go to the geometric tolerance. It says create a flatness call out on the bottom surface. There's the bottom surface. I place the call out. I go grab flatness, which is right there. And I forgot the number for 13 was 6 thousandths. We'll type in 0.006. And what datum do I put in here? Well, let's go look at the sheet. The sheet right here says flatness tolerance. Let's go scroll up here. Near the top here somewhere. There it is right there. Flatness there's the symbol. That's the characteristic symbol for the feature control frame. Here's an example of a call out. Flat within 4 thousandths. And then there's the tolerance zone, 2 parallel perfect planes that are 4 thousandths apart. And it says datum used, it says no. So straightness, flatness, circularity, cylindricity, these are all form types of characteristics. And none of these need a datum. Well, how can that possibly be? Well, think about it. What are we saying? We're saying that this flat surface is flat to what? It's flat to itself. There is no datum reference needed because it's not flat to any of the datums. It's just flat to itself. So flatness doesn't need a datum. So if you put a datum on here, again, the manufacturer and the inspector and the quality control person is going to say, This doesn't make any sense. If you put a datum on here, it's not flat to a datum, it's flat to itself. So now let's go to the next bullet here. So the next bullet says, create a parallel callout to the top surface within tolerance zone on the Blackboard handout. Okay, so let's go to the Blackboard handout. For VIBA, we're doing her thing here. VIBA is 13. Parallel tolerance is 4 thousandths. So I want to make this top surface parallel based on the instructions I give you. Make that parallel to datum A within 4 thousandths. So I'm going to click that face. I'm going to click there. I'm going to go choose parallel. Where is it? Parallel within 4 thousandths. This one needs a datum. Why does it need a datum? Because this sheet says it needs a datum. This sheet right here that we keep going back to that I love so much, if I can find it, says it needs a datum. And it's parallel to datum A. So let's go find this. Where's this GD&T thing? Oh, here it is. So parallel is right here. Parallelism, there's a symbol, there's an example, there's the definition of the tolerance zone, and it says, does it need a datum? And it says, yes, absolutely. So it makes sense because you're parallel relative to another datum, and in this case, you're parallel relative to datum A. And so that takes care of the 4 feature control frames I'm asking for. And then I've gone over my 1 hour thing by 10 minutes here. But I think that takes care of the other miscellaneous notes. Typical stuff, revision block, title block, make it 11 by 17 PDF plot. All basic dimensions should originate from the datums. That's what we talked about earlier. All right, so I'm going to stop recording this thing so it doesn't get to be a 3-hour video. And then we'll talk about assigning